Welcome to DAR Tutors. Today, we will explore key concepts in IB Chemistry Higher Level, focusing on molecular bonding and the analytical technique of chromatography. Our objective is to build a strong foundation in these advanced topics. We will cover two main areas. First, the principles of chromatography and the calculation of RF values. And second, advanced bonding theories, including sigma and pi bonds, hybridization, and resonance. Let's begin with chromatography. Chromatography is a powerful technique used to separate the components of a mixture. The fundamental principle involves a mixture passing through a medium where its components move at different rates. This differential movement is crucial for separation. It's like a race where different participants have different affinities for the track and the wind. To understand this, we need two key phases: the stationary phase and the mobile phase. The stationary phase is a fixed, solid material, or a liquid immobilized on a solid support. The mobile phase is a liquid or gas that moves through or along the stationary phase. Separation occurs as the components of the mixture, also known as the analyte, partition or distribute themselves between these two phases. When a substance is more attracted to the stationary phase, it will move more slowly. Conversely, if it is more attracted to the mobile phase, it will move more quickly. This process of the mobile phase moving through the stationary phase is called elution. The primary types of interaction are adsorption and partitioning. Adsorption involves the analyte molecules sticking to the solid surface of the stationary phase. Partitioning, as we will see, involves the analyte distributing between a liquid stationary phase and a moving solvent. Let's apply these principles to a specific type: paper chromatography. This technique is a form of partition chromatography. In paper chromatography, the stationary phase is the water molecules hydrogen bonded to the hydroxyl groups on the cellulose of the paper. The mobile phase is a liquid solvent or a mixture of solvents. The process is initiated by placing a small spot of the mixture near the bottom edge of a strip of chromatography paper. The paper is then placed in a vessel containing the mobile phase, ensuring that the solvent level is below the applied spot. The solvent moves up the paper by capillary action, eluting the components of the mixture. Separation occurs as the substances in the mixture partition themselves between the stationary water and the moving solvent. This partitioning is governed by the polarity of the components. A more polar component will be more attracted to the polar stationary phase, spending more time in the water layer and thus moving more slowly up the paper. A less polar component will be more soluble in a less polar mobile phase, spending more time in the solvent and thus moving faster. The rate of elution is constant for a given substance in a specific system. This is because equilibrium is never fully reached, as fresh solvent is continuously moving up the paper. A more advanced technique, closely related to paper chromatography, is thin layer chromatography, or TLC. In TLC, the stationary phase is a uniform thin layer of fine particles, typically silica, SiO2, or alumina, Al2O3, spread on an inert support like a glass plate. The process is experimental techniques-wise very similar to paper chromatography. A small spot of the sample mixture is applied near the bottom edge of the plate. The plate is placed in a chromatography tank with a solvent. As with paper chromatography, the solvent is drawn up the dry surface by capillary action, eluting and separating the compounds based on their differential affinities for the stationary and mobile phases. TLC offers several significant advantages over paper chromatography, which is why it is widely preferred in organic chemistry. First, the chromatograms develop much more quickly. Second, TLC gives better resolution, meaning a better separation of the components in a mixture. And third, the results are generally more reproducible and easier to interpret. If the components are not colored, they can be visualized using several methods. Commonly, UV light is used, which causes the spots to fluoresce. Alternatively, a chemical indicator such as ninhydrin for amino acids can be sprayed on the plate to develop visible colored spots. To make chromatography a quantitative tool, we use the retardation factor, or RF value. The REF value is a characteristic property of a compound in a given chromatography system. It is defined by a simple ratio: the distance traveled by a given component spot divided by the distance traveled by the solvent front, both measured from the starting line. Let's work through an example. Imagine in a TLC experiment, the solvent travels 38 millimeters from the starting line to the solvent front. A particular component in the mixture travels 22 millimeters. To find its RF value, we divide the spot distance by the solvent distance. So 22 divided by 38 gives us 0.58. The RF value is always less than or equal to 1, as the component can never travel further than the solvent. A key takeaway is that the RF value is a ratio and is therefore independent of the total distance the solvent travels. It does depend, however, on the nature of the stationary and mobile phases, the compound itself, and temperature. RF values are incredibly useful for identification. If you run an unknown sample alongside a known reference compound and they produce spots with the same RF value, it is strong evidence that they are the same compound. Scientists also use tables of RF values obtained under standard conditions to identify unknown substances. One practical application is to monitor the progress of a chemical reaction. You can take small samples from the reaction mixture at different times and run TLCs, comparing them to the starting material and the expected product. This allows you to track the disappearance of reactants and the formation of products. We will now transition to our second major topic, advanced bonding theories. While Lewis structures and V-SEP theory are excellent for predicting molecular shapes, they are simplified models. To understand why bonds form and why molecules have their specific shapes and properties, we need to introduce molecular orbital theory. Molecular orbital theory describes how the atomic orbitals of individual atoms combine and merge to form new orbitals that belong to the entire molecule, called molecular orbitals. This process leads to the formation of different types of covalent bonds. In covalent bonding, atomic orbitals overlap. We are particularly interested in two types of overlap that lead to two distinct types of bonds. The first is the sigma bond, denoted by the Greek letter sigma. A sigma bond is formed by the head-on or axial overlap of atomic orbitals. This overlap occurs along the imaginary line connecting the two nuclei. The electron density is concentrated directly between the two nuclei and along this bond axis. A pi bond, denoted by the Greek letter pi, is formed differently. It involves the sideways or lateral overlap of parallel p orbitals. This overlap occurs above and below the plane of the two nuclei. The electron density of a pi bond is therefore not on the bond axis itself, but in two lobes, one above and one below. The greater the overlap between the atomic orbitals, the stronger the resulting covalent bond. The amount of overlap is a direct measure of bond strength. Let's formalize the differences between sigma and pi bonds. Understanding these distinctions is fundamental to predicting the properties of molecules. The sigma bond is formed by head-on overlap. It can be formed from SSSP-PPP or hybridized orbital overlaps. Pi bonds, on the other hand, are formed by the sideways overlap of parallel p orbitals only. Because the head-on overlap in a sigma bond is more effective, sigma bonds are stronger. The sideways overlap of pi bonds is less effective, making them inherently weaker than sigma bonds. Another crucial difference is rotation. Sigma bonds are rotationally symmetrical, allowing free rotation of the atoms around the bond axis. Pi bonds, however, are formed from sideways overlap. Free rotation would break this overlap, which requires a significant input of energy. Therefore, pi bonds restrict rotation. This restriction on rotation by pi bonds is the reason for geometric isomerism in alkenes, like cis and trans isomers. Finally, remember that pi bonds can never exist on their own. They must always be accompanied by a sigma bond. A single bond is a sigma bond. A double bond consists of one sigma and one pi bond. A triple bond is one sigma bond and two pi bonds. The overall shape of a molecule is determined by its sigma bond framework and any lone pairs, not by the pi bonds. Let's apply this to a worked example, describing the formation of the oxygen molecule, O2. First, we write the electron configuration for an oxygen atom. Oxygen has 8 electrons. Its configuration is 1s2, 2s2, 2p4. The valence electrons are in the 2s and 2p subshells. In the 2p subshell, 2 orbitals are half filled with 1 electron each. These are the orbitals that will participate in bonding. Now let's consider the bonding between 2 oxygen atoms. We have 2 oxygen atoms, each with 2 unpaired electrons in its p orbitals. One of these half-filled p orbitals from the first oxygen atom will overlap head-on with a half-filled p orbital from the second oxygen atom. This forms a sigma bond. The electron density is concentrated along the internuclear axis. So far, we have a single bond, but we know the oxygen molecule has a double bond. The other half-filled p orbital on the first oxygen atom is perpendicular to the sigma bond axis. It will overlap sideways with the corresponding half-filled p orbital on the second oxygen atom. This sideways overlap forms a pi bond, with electron density above and below the sigma bond. Therefore, the oxygen molecule, O2, is formed by one sigma bond and one pi bond, resulting in a stable double bond. The pi bond contributes to the overall strength of the double bond and restricts rotation between the two oxygen atoms. We have successfully explained the double bond in O2 using MO theory by identifying the sigma and pi bonds. While sigma and pi bonds explain a lot, they don't fully explain the observed structures of many simple molecules. This led to the development of another theory, hybridization. Hybridization is the concept of mixing two or more atomic orbitals to form an equivalent number of new hybrid molecular orbitals. These hybrid orbitals have a different shape and energy than the original atomic orbitals and are much better suited for forming covalent bonds with specific geometries. Why is this necessary? Consider methane, CH4. VSEPR theory predicts a tetrahedral shape with 109.5-degree bond angles. A carbon atom in its ground state has the configuration 1s-22s22p2. It has two unpaired electrons in its p orbitals, and these p orbitals are oriented at 90 degrees to each other. If it bonded using these, we'd expect a bent molecule, not a tetrahedral one. We also wouldn't expect it to form four identical bonds. Hybridization solves this problem. First, one of the paired 2's electrons is promoted to an empty 2p orbital requiring energy. This gives carbon four unpaired electrons. Second, the 2's in all three 2p orbitals mix to form four new identical sp3 hybrid orbitals. These orbitals are directed towards the corners of a tetrahedron at 109.5 degrees to each other. These four sp3 hybrid orbitals of the carbon atom can now overlap with the 1s orbitals of four hydrogen atoms to form four identical sigma bonds. The result is the observed tetrahedral shape of methane. The initial energy cost of promoting the electron is more than offset by the energy released from forming two additional stronger CH bonds, leading to a more stable molecule. Beyond sp3 hybridization, carbon atoms can also undergo other types of hybridization, depending on their bonding arrangement. These lead to different geometries and bond types. We will now discuss sp2 and sp hybridization. These are crucial for understanding the structure of alkenes, alkynes, and carbonyl compounds. Let's consider ethene, C2H4, which has a double bond and a trigonal planar geometry at each carbon. Here, carbon is still promoted to the 1s22's 12p3 state. However, only the 2s orbital and two of the three 2p orbitals hybridize. This creates three identical sp2 hybrid orbitals, which are arranged at 120 degrees in a trigonal planar fashion. One 2p orbital on each carbon atom is left unhybridized and is oriented perpendicular to this plane. How does this form ethene? One sp2 orbital from each carbon overlaps head-on to form a CC sigma bond. The remaining sp2 orbitals on each carbon overlap with 1s orbitals from hydrogen atoms to form CH sigma bonds. Then the two unhybridized 2p orbitals, which are parallel, overlap sideways to form a pi bond. So, the double bond in ethene consists of one sigma bond and one pi bond, and the sp2 hybridization explains the trigonal planar geometry around each carbon. What about ethene, C2H2, with a triple bond and a linear geometry? Here, carbon undergoes sp hybridization. One 2s orbital hybridizes with only one 2p orbital to form two sp hybrid orbitals, which are arranged linearly at 180 degrees. This leaves two 2p orbitals unhybridized on each carbon. For ethine, the two sp orbitals on each carbon are used to form a CH sigma bond and a CC sigma bond. The two unhybridized 2p orbitals on one carbon overlap sideways with the corresponding unhybridized 2p orbitals on the other carbon to form two pi bonds. The triple bond in ethene is therefore composed of one sigma bond and two pi bonds, and the sp hybridization dictates the linear structure. We can summarize the three types of carbon hybridization and connect them to VS-Epper theory and the Lewis structure of the central atom. A key concept for applying VS-EPR theory to determine hybridization is the idea of electron domains. An electron domain is a covalent bond, whether single, double, or triple, or a non-bonding lone pair of electrons. It's a region of high electron density. The number of electron domains around a central atom directly determines its hybridization state. Let's use a summary table to tie everything together. If a central atom has 4 electron domains, it has sp3 hybridization, like in methane. This could be 4 single bonds, or 3 bonds and 1 lone pair, like in ammonia, or 2 bonds and 2 lone pairs, like in water. If there are 4 electron domains, the hybridization is sp3. This gives a tetrahedral electron geometry, and the molecular geometry is determined by how many of those domains are lone pairs. If there are 3 electron domains, it's sp2 hybridized. A common case is 3 single bonds, which results in a trigonal planar geometry, like in BF3, or a carbon in ethene. But it could also be a double bond and 2 lone pairs, which would give a V-shaped geometry. The key is 3 domains for sp2. Finally, if there are only 2 electron domains, the atom is ep-hybridized, giving a linear geometry. This can be a triple bond and a single bond, like in ethene or the nitrogen molecule, or 2 double bonds, like in carbon dioxide. The central carbon in CO2 is sp hybridized because it has 2 electron domains, the 2 double bonds. Our final topic for today is resonance, another essential concept in describing the bonding in many molecules and polyatomic ions. Resonance occurs when the true structure of a molecule or ion cannot be represented by a single Lewis formula. Instead, we must draw 2 or more Lewis structures, called resonance structures, and consider the true structure to be an average or hybrid of all of them. This is a common misconception, so pay close attention. Resonance structures do not exist in an equilibrium with each other. The molecule is not constantly switching between the structures. The resonance structures are hypothetical, imaginary representations that we use to describe a single real structure, the resonance hybrid, which is an average of all of them. Think of it like describing a mule, which is a hybrid of a donkey and a horse. You wouldn't say the mule is sometimes a horse and sometimes a donkey. It is always a mule, a unique animal with characteristics of both parents. A more appropriate term, derived from molecular orbital theory, is delocalization. The resonance structures are our attempt to describe the reality of delocalized electrons, where electrons are not confined to a single bond or atom, but are shared among several atoms. In the resonance hybrid, these delocalized pi electrons form a continuous electron cloud. Let's illustrate resonance with a classic example. The ozone molecule, O3. We can draw 2 plausible Lewis structures for ozone. Structure 1 shows a double bond on the left and a single bond on the right, with formal charges of -1 on the terminal oxygen and +1 on the central oxygen. Structure 2 shows the same arrangement, but with the double bond on the right. Notice that these structures are identical except for the position of the pi bond. These 2 Lewis formulas are the resonance structures. The real ozone molecule does not look like either of them. The experimental evidence confirms this. X-ray analysis shows that both oxygen-oxygen bonds in ozone are of the same length, 0.128 nanometers. This is intermediate between the typical length of an oxygen-oxygen double bond, 0.121 nanometers, and an oxygen-oxygen single bond, 0.132 nanometers. This proves that the bonding in ozone is not alternating single and double, but is instead averaged between the 2 structures. We represent this real structure as a resonance hybrid. Here, dashed lines indicate that the partial pi bond character is shared equally between the 2 oxygens. The formal charges are delocalized, with a positive charge on the central oxygen and a partial negative charge of -1/2 on each terminal oxygen. The bond order for each oxygen-oxygen bond is 1.5, representing a bond that is stronger than a single bond, but weaker than a double bond. From a molecular orbital perspective, this delocalization arises from the sideways overlap of the unhybridized 2p orbitals on all 3 oxygen atoms. Instead of forming a localized pi bond between just two atoms, the electrons are spread over a larger delocalized pi molecular orbital that encompasses the entire O3 molecule. Let's look at another important example, the carbonate ion, CO32. The carbonate ion has a central carbon atom bonded to 3 oxygen atoms. We can draw 3 equivalent Lewis structures that satisfy the octet rule. In each structure, there is 1 CO double bond and 2 CO single bonds, with formal charges of 1 on the single bonded oxygens and 0 on the double bonded oxygen. The only difference between these structures is the position of the CO double bond. Therefore, the actual structure of the carbonate ion is a resonance hybrid of these 3 forms. All 3 CO bonds are identical, with a bond length intermediate between that of a single and a double bond, and each oxygen atom carries a partial negative charge of -2/3. This delocalization of electrons is visualized as a continuous pi cloud extending over all 4 atoms, above and below the trigonal planar molecule. This delocalization provides significant stability, a concept known as resonance energy. Resonance energy is the energy difference between the hypothetical energy of one resonance structure and the observed energy of the actual, more stable resonance hybrid. The greater the number of high-quality resonance structures a molecule can have, the greater its resonance energy and the more stable it is. To form a stable resonance hybrid, the resonance structures you draw must follow 4 strict rules. These rules ensure that the structures are chemically valid and contribute meaningfully to the hybrid. First, all resonance forms must have the same spatial arrangement of atoms. This means the overall molecular shape must be identical in all structures. Second, no resonance form for period 2 atoms like carbon or oxygen can have more than 8 valence electrons around them, no expanded octets. Third, all resonance forms must contain the same total number of electron pairs, both bonding and non-bonding. Electrons are simply repositioned. And fourth, all resonance forms must carry the same overall total charge as the original molecule or ion. In the case of ions, we have additional guidance for determining which resonance structures are more important. Structures with negative charges on the more electronegative atoms and positive charges on the less electronegative atoms are generally more stable and contribute more to the resonance hybrid. In neutral molecules, structures with the minimum number of formal charges and where all atoms have a complete octet are typically the most significant. Generally, the more stable the resonance structures, the greater their contribution to the overall hybrid stability. Let's apply resonance to some organic chemistry contexts. First, the ethanoate ion, CH3CO. In the ethanoate ion, we can draw 2 equivalent resonance structures. In one, the oxygen on top forms a double bond. In the other, the oxygen on the bottom forms the double bond. These are completely equivalent. Because they are equivalent, they contribute equally to the resonance hybrid. This means the negative charge is delocalized over both oxygen atoms, and the 2 carbon-oxygen bond lengths are identical and intermediate between a single and double bond. This stabilization is why ethanoic acid is a much stronger acid than ethanol. The ethanoate ion conjugate base is stabilized by resonance, making it less reactive and more likely to form. Next, consider propanone, the simplest ketone, CH3COOH3. Propanone has a polar carbonyl group. We can draw 2 resonance structures for it. The major one is a neutral molecule with a Ca-CTO double bond. A minor but important structure is created by moving the pi electrons to the more electronegative oxygen, giving it a negative charge and leaving a positive charge on the carbon. This minor resonance structure contributes to the overall resonance hybrid, resulting in a partially positive carbon atom and a partially negative oxygen atom. This explains the observed polarity of ketones and, critically, why the carbon atom in the carbonyl group is an electrophile. It is susceptible to attack by electron-rich species called nucleophiles. We have now reached the 10-minute mark. If you find these explanations helpful and want to delve deeper into IB chemistry or other subjects, we invite you to contact DAR Tutors for expert tuition. We offer personalized online and home tuition for IB, A-Level, and IGCSE curricula to help you achieve your academic goals. Now let's continue with another crucial application of resonance, the bonding in benzene. The structure of benzene, CCH6, has been a source of fascination and debate for centuries. The benzene molecule can be described by 2 equivalent resonance structures. Each structure is a ring of 6 carbon atoms, with alternating single and double bonds. Experimental evidence, namely X-ray diffraction, shows that all 6 carbon-carbon bonds in the benzene ring are identical. Their length, 140 picometers, is intermediate between a typical CC single bond, 154 pm, and a CC double bond, 134 pm. This again is characteristic of a resonance hybrid where the electrons are delocalized. A molecular orbital model explains this beautifully. Each carbon in the ring is sp2 hybridized, forming a trigonal planar framework. This leaves one unhybridized 2p orbital on each carbon perpendicular to the ring. These 6 parallel p orbitals overlap sideways to form a continuous cyclic delocalized pi molecular orbital. The 6 pi electrons are not localized in specific double bonds, but are spread out over the entire ring. The delocalized pi system and the high resonance energy are responsible for benzene's unique and surprising properties. Alkenes with their localized pi bonds readily undergo addition reactions, where the pi bond breaks and new single bonds are formed. Benzene, despite having Pa bonds, is remarkably unreactive. It does not undergo addition reactions under normal conditions, such as reacting with bromine without a catalyst. Why? Because an addition reaction would destroy the stable, delocalized pi system, costing a large amount of energy. Instead of addition, benzene undergoes substitution reactions. In these reactions, one of the hydrogen atoms is replaced by another group, but the delocalized pi system is preserved. This mechanism allows benzene to react while retaining its high resonance energy, making it kinetically more stable than you might expect. This demonstrates how the theoretical model of resonance and delocalization directly explains experimental observations about chemical behavior. Let's work through a few additional examples to solidify your understanding of these advanced bonding concepts. First, we will draw the resonance structures for the nitrate V ion, NO3, and determine the bond order and charge on each oxygen atom. The nitrate ion has a central nitrogen atom with 2 oxygen single bonds and 1 oxygen double bond. The 3 equivalent resonance structures are formed by moving the pi bond around the ring of NO bonds. In each structure, the double bonded oxygen is neutral, while the 2 single bonded oxygens have a formal charge of H1. The nitrogen has a formal charge of Pla1. In the resonance hybrid, the Pa bond is delocalized over all 3 NO bonds. The bond order is calculated as the total number of bonds, 4, divided by the number of bonding locations, 3, which is 4,3. The total charge of 1 is distributed over the 3 oxygens, so each oxygen carries a partial charge of 1,3. The actual NO bond length is therefore intermediate between a single and a double bond. Now for our second example, explain why penta-1,4-DNA does not contain any delocalized pi electrons, whereas penta-1,3-DNA does. Let's start with penta-1004-DNA. This molecule has 2 pi bonds separated by 2 single bonds, which contain sp3 hybridized carbon atoms. These sp3 carbons do not have unhybridized p orbitals available for lateral overlap. Because the pi bonds are interrupted by sp3 carbons, their p orbitals cannot overlap to form a continuous delocalized system. Therefore, the pi electrons are localized to their respective double bonds. Now let's look at penta-1,3-DNA. This molecule has 2 pi bonds separated by only 1 single bond. All 4 carbon atoms involved are sp2 hybridized. Each of these sp2 carbons possesses an unhybridized p orbital, all of which are parallel to each other. This allows for continuous lateral overlap along the entire 4-carbon chain, creating a delocalized pi system. The pi electrons are not confined to the 2 original double bonds, but are spread over the larger conjugated system, leading to increased stability. The last worked example we'll cover involves comparing bond lengths in propanoic acid and the propanoate ion. The question asks us to explain why the 2 carbon-oxygen bond lengths in propanoic acid C2H5COOH are different, but the 2 CO bond lengths in its conjugate base, the propanoate anion C2H5SO, are the same. First, let's consider propanoic acid. The structure contains a carbon atom double bonded to one oxygen and single bonded to another oxygen as part of the carboxyl group. In propanoic acid, the bonding is best described by a single Lewis structure, not multiple resonance structures. There is a distinct C-A-CO double bond and a CO single bond. A double bond is shorter and stronger than a single bond due to the pi bond's contribution. Therefore, we would expect the CO bond length to be shorter than the CO bond length, which is what is observed experimentally. Now, let's analyze the propanoate anion C2H5COO, which is formed when propanoic acid loses a proton. The propanoate anion can be described by two equivalent resonance structures. The pi bond is delocalized over both carbon-oxygen bonds, and the negative charge is distributed over both oxygen atoms. As a result, the actual structure is a resonance hybrid. The two carbon-oxygen bonds in the propanoate anion have a bond order of 1.5, meaning they are identical in length. This length is shorter than a CO single bond but longer than a CO double bond. This stabilization of the conjugate base through resonance is why carboxylic acids like propanoic acid are acidic. Let's finish with some IB-style practice questions to test your understanding. First question. A chromatography experiment is performed with a solvent front distance of 14.0 centimeters and a spot travel distance of 9.8 centimeters. Calculate the RF value for the spot. Take a moment to solve this. The solution is as follows. The RF value is the distance of the spot divided by the distance of the solvent front. That is, 9.8 centimeters divided by 14.0 centimeters. This gives us an RF value of 0.70. Note that RF values have no units as the units cancel out. Second question. Predict and explain the hybridization of the nitrogen atom in the ammonia molecule, NH3. Pause the video and think about this one. To solve this, we first need to determine the number of electron domains around the central nitrogen atom. Nitrogen is bonded to 3 hydrogen atoms, giving 3 bonding domains. It also has 1 lone pair, for a total of 4 electron domains. 4 electron domains correspond to sp3 hybridization. The nitrogen atom is sp3 hybridized, creating 4 hybrid orbitals. 3 of these form sigma bonds with hydrogen, and 1 accommodates the lone pair, resulting in a trigonal pyramidal molecular geometry. Let's continue with 2 more practice questions. Third question. State and explain 2 advantages of thin layer chromatography over paper chromatography. Think back to our discussion earlier. There are several correct answers here. The stationary phase in TLC is more robust than paper, allowing for the use of more aggressive visualization agents that might destroy paper. Additionally, TLC generally offers better resolution, meaning a clearer separation of spots. It also typically has shorter development times, allowing for faster analysis. Fourth question. Explain why the nitrogen molecule, N2, is highly unreactive. This question requires combining concepts of bonding and energy. The nitrogen molecule contains a triple bond. Let's analyze this bond. According to molecular orbital theory and hybridization, each nitrogen atom is sp hybridized. It forms 1 sigma bond along the internuclear axis and 2 pi bonds from the sideways overlap of the 2 unhybridized p orbitals. This results in a very strong bond, with a high bond enthalpy of 945 kilojoules per mole. The large amount of energy required to break this bond makes the nitrogen molecule very stable and unreactive. Our final practice question is a more complex problem combining VSEPR theory, hybridization, and molecular shape. The question asks us to draw the Lewis structure for the nitride ion, NO2, predict the hybridization of the central nitrogen atom, and describe its molecular geometry. Let's break this down step by step. First, we find the total number of valence electrons. Nitrogen has 5, each oxygen has 6, and the negative charge adds 1 electron. That's a total of 18 valence electrons. Next, we connect the nitrogen to the 2 oxygens with single bonds. We complete the octets on the oxygens, which uses up 16 electrons. The remaining 2 electrons form a lone pair on the nitrogen. The nitrogen currently has only 6 electrons, so we form a double bond with one of the oxygens. This gives two possible resonance structures. In the resonance hybrid, the nitrogen forms two bonds to oxygen and has one lone pair. So it has three electron domains, two bonding domains, and one lone pair. Three electron domains correspond to sp2 hybridization. This gives a trigonal planar electron geometry. The molecular geometry, however, is determined only by the bonded atoms. With one lone pair and two bonded atoms, the molecular geometry is bent or V-shaped. The bond angle will be slightly less than the ideal 120 degrees due to the lone pair bonding pair repulsion. Let's quickly recap what we've learned today. We started with chromatography, a powerful separation technique based on differential partitioning between a stationary and a mobile phase. We learned how to perform TLC and how to calculate and use the RF value for identification and analysis. We then moved on to advanced bonding concepts, starting with molecular orbital theory. We described the formation of sigma and pi bonds and their fundamental differences in terms of overlap, strength, and ability to rotate. We introduced hybridization, explaining how sp, sp2, and sp3 hybrid orbitals form, and how to determine the hybridization state from the number of electron domains. Finally, we explored resonance, the concept of representing a single molecular structure as a hybrid of multiple Lewis forms, which we now understand as a way to describe the delocalization of pi electrons. We saw how this delocalization explains the stability of ions like ethanoate and nitrate, and the unique properties and unreactivity of benzene. Mastering these concepts is crucial for success in IB chemistry. Thank you for joining.